Okay, so I think we can start. So my name is Javier, and today we have a kickoff webinar on the ALEX17 Diurnal Cycles benchmark. As you probably know, this is coordinated within the IEA Win Task 31. And today I'm hosting this session together with Pedro Santos from DTU and Roberto Chavez, also from CENER. So we have a presentation that will give you an overview of the different benchmarks that we are planning to run in the next year or so around the ALEX test site. And more specifically, the one that is related to Diurnal Cycles, which will be presented by my colleagues Pedro and Roberto. So maybe we'll go through the presentation, which is maybe a half hour long. And during this time, I would like to ask you to switch off your microphones for a better audio. We will be recording the session so that we can distribute this afterwards through YouTube. Yeah, so let's get started. So this is the ALEX mountain range. You see there is a kind of a large mountain where CENER has its complex terrain test site for providing prototypes. And we've been running this site for more than 10 years now. And when we think about the kind of campaigns we have at this site, the main one would be this long-term reference that we established at one of the reference positions, MP5. Just to give you an overview of the test site, it currently has four of these MP positions. These are 118 meters high met mass, which are right in front of the turbine stands where we have our prototypes. Farther to the south, you see we have some operational wind farms from Acciona. The terrain elevation tells you that this is around 1,000 meters high, and the valley right in front is around 700 meters. So you have quite a nice elevation change there. You also see the wind climate distribution, which is giving you a pretty smooth variable distribution with two prevailing wind directions from the north, which is what we call the clean sector. So that's the main sector that the test site was designed for. But we also have a quite important component from the south, which we could call the dirty sector, which includes all the wake effects from the turbines. And this is what you can see in this graph. So the panel on the left gives you the northern sector in terms of wind conditions on wind shear, turbulence intensity, and vertical components. And the panel on the right is for the southern wind conditions, all measured at the MP5. And as you can see, we have different wind conditions depending on stability, which in this case we measure with a fruit number. And so this is what we see every day at the test site. And with the opportunity of the European Wind Atlas project, we wanted to run a campaign in front of the mountain range, in the valley right in front, to see how we could explain these wind conditions by understanding better what's going on in the valley in front of us. So that's kind of the objective for today's presentation, to speak about this NIWA campaign. But before that, I also want to explain about another interesting campaign that happens mostly in 2010, which is related to the site calibration of the test site. So this is what you do when you want to operate a test site. You want to have the conditions of the reference mass being related to the positions where you plan to have the turbines. So this is what we did in the site calibration campaign, doing pairs of observations between reference metmast and turbine metmast, and then mapping the flow correction factors that happen in between. So I mentioned this because there will be a benchmark on numerical site calibration that will focus on this specific period of the test site. Now this is the NIWA campaign. It's also a year long, even a year, if you include the surface observations. And Pedro will explain more about this, but essentially we are deploying a number of instruments in the valley and also in the northern ridge to really understand the influence between these mountain and valley flows for different wind conditions, different seasons of the year, and trying to see what's happening with profile, mast measurements, as well as scanning LiDAR and solar equipment. This is all summarized in this nice blog post that you can find already. Just to give you an overview of the benchmarks that we are planning to launch in the next months, starting today with the Diurnal Cycles benchmark that Pedro will discuss, and Roberto, where the objective is to understand the inflow conditions from the north, and where we designed the benchmark thinking about meso-micro type of modeling for wind conditions. And then the numerical site calibration, which is another benchmark led by Stefan Sinclair from Metrodyne, where the focus will be on this short-term site calibration campaign from 2010, where we try to replicate what the standard says about site calibration, trying to reproduce that with modeling. And the focus there is, of course, the flow correction factors that are important for site calibration. We also want to complete this set of benchmarks with one on annual energy production, which was already introduced during the NIWA project with the Rodeserberg benchmark. And here the idea is to try to reproduce a year worth of statistics on wind conditions as well as AEP, and eventually not only for LIS but also for other sites like Rodeserberg in Germany and Perdigão in Portugal. So this is the plan for using LIS data, and with this I turn this over to Pedro, who will give you more information about the ALEX17 campaign and how we are using that to set up the Diurnal Cycles benchmark. So Pedro, over to you.
Yes, thanks, Javier. And I hope you all can also see my screen now. And I'd like to thank also our colleagues from the other side of the Atlantic to be here. It's a bit early there. And my part then is to explain a little bit more about the ALEX17 experiment. So we're going to go through the experimental layout, and also I plan to present a little bit of the validation data and the period that we chose to propose the Diurnal Cycle benchmark, and also what we have in terms of measurements for validation of the models. So the campaign itself, it's summarized also already in a blog post that Javier mentioned. And as you could see from the introduction, is a large scale and inhomogeneous topography, and also in terms of land cover. And during the 2 years from 2017 to 2019, we have deployed a number of experiments, of equipments, and all the equipments were concurrently measured during 7 months, including all the surface stations, scanning lidars, and the mat masts. So basically, during these 7 months, we were looking for a period that could be both favorable in terms of synoptic conditions, but also in terms of data availability of the instruments to propose. So the diurnal cycle benchmark, it's going to be presented here. It's a 96-hour period. And as Javier mentioned, we are considering the northerly winds to be the clean sector, and that would be the period that we're going to show here. So I'm calling this northerly winds case. And it's basically a case that we're going to see from the measurements with northerly winds on top of the mountain and recirculation zones, and also some flow blockage in the windward side of the mountain. So we already have published a campaign and data report. So if you want to see more technical details of what we are going to show here in the presentation, you could relate to that. And also we already have the metadata and some links to access all the experimental data set, also in the link below. So we can see here the digital elevation model. That is one of the inputs for this benchmark. It's a 2-meter resolution map, 10 by 10 kilometers in area. And the wind rolls shows the prevailing wind on top of the mountain at MP5 during the 1 year that we had the extensive measurement period. The mountaintop and the Tajonar Ridge, there is a 6 kilometers north. They are not parallel. And also the prevailing wind, it's oblique to these topographic features. So yeah, we could say that it's a complex flow, both inside the valley and also on top of the ridge and on top of the mountain. And to study that, we have deployed 5 wind scanners. And this is the yellow dots, WLS1, 2, 3, 4, and 5. And they are combined in such a way that we have planned a measurement that is in this Z shape, and I'm going to show a little bit how we did that. So the reference at MP5, as we already saw, is given by the 180-meter mast equipped with 3D sonics. And in the valley, during the intensive observational period, we have deployed 6 80-meter mat masts. And this is the green dots that you can see on the map. 4 of them are equipped with 3D sonics, and 2 of them are regular IAC compliant cup masts. And the Z-shaped transect line that we can see, the combination of the red lines and the blue transect line, it's basically allows us to give 2D or 3D reconstruction of the wind. So in the red lines on top of Tajonar and on top of the Alaís mountain, we have a combination of 2 scanners. So WLS1 and 3 are doing a dual Doppler on top of the north ridge, and number 2 and number 4 a dual Doppler on top of the south ridge. And we have also in the blue line, we have 4 scanners, so 2, 3, 4, and 5. They are concurrently measure the blue line. And we are doing these scanning strategies every 1 hour. We repeat scanning strategy in order that we can have at least 1 10-minute period every half an hour in this Z transect line. So this is also one of the validation data that we want to propose for the modelers to be able to compare with. Then in the blue line that we saw on the map, it's basically formed by the combination of WLS3 and 5 So the blue transect line, we can see a picture of the site. And in the map below, we can see this cross section connecting number 3 and number 5, where we actually have RHI scans. So we have a vertical plane where it's actually quite useful to have an idea of the flow approaching at the ALEX mountain. So it's the combination of 2 RHIs, as I said, and it's also a possible validation data, since we have on this red area, there is the superposition of the 2 RHIs. We have the line of sight wind speed that can be also be used. And looking at this scans, we could actually select the period and see the main flow patterns that we observed at the site. And this would be recirculation zones on the lee side of the north ridge, and also a flow blockage when we have northerly winds, a blockage in the windward side of the ALEX mountain. So we're going to see some results. The table that you see in this slide is the UTM coordinates of the 2 scanners, so that it's possible for you to actually reconstruct this vertical plane. So the northerly wind case that we are proposing in this diurnal cycle benchmark is composed of 96 hours going from the 30th of September of 2018. I'm sorry, I have to correct the year here. I'm going to do it in the slide, but it's the 2018 and going to the 4th of October of 2018. So it's last year and not this year. Sorry for the mistake. And what we can see from the wind roses, so the 2 wind roses are the average wind roses in this period. And we can see that actually the top of MP5 has a quite different wind regime from the valley. So we actually have a turning of the wind. We have a northwesterly winds in the valley, and that is actually deflected approaching to the mountain and speed up to have a northerly winds in the mountaintop. So we are proposing 3 sets of validation data coming from the measurements during this period. First is vertical profiles at all the mass positions. So we have 6 positions with vertical profiles that are actually going to be readily available for you to verify this period. And the other proposed validation data is actually the wind vectors, so the dual Doppler and triple Doppler reconstructions on the 10-kilometer Z transit. And the third one is the vertical plane that we have seen before in the transect line, so in the blue line in the map. Okay, so the time series on top of the MP5 can be seen on this plot. We have on the top one the wind speed at the MP5, and then wind direction in the middle plot, and the temperature from temperature sensors in the bottom one. And I think what we can take away from here is that we have an increase in wind speed from the 30th to the 1st. The 1st of October is, let's say, the more stationary day with high wind speeds on top of the mountain. The whole 96 hours period can be seen as having a really constant wind direction, at least at the mountaintop. And from the 2nd and the 3rd of October, we also start seeing shear and a more intensified stratification daily cycle. And this is the regime on the mountaintop. Once we go to the valley, things change quite a bit. So what we see here is one of the masts, the M7, there is in the middle of the valley floor. And then we can see a quite big variation, really low wind speeds in the first daily cycle, which catches up in the second day. So the 1st of October is the day with the highest wind speeds. And then the 2nd of October and 3rd are also, we can see a big daily regime, and periods with a constant wind speed, wind direction in the valley floor. We can see that the 1st of October is the day in terms of wind direction, the more stationary. And in the bottom plot, what we can see is in blue, the sensible heat flux, and in orange, the net radiation measured by an energy balance station, also in the same position. So although the 1st of October is the high wind speed daily cycle with a constant wind direction, is also the day with no clear sky conditions. So I think that has to be balanced, and I think it'd be nice to have a discussion later on which would be, if we had to pick one day due to computational effort, what would be the, let's say, the best day to prioritize in the simulations. So I hope this idea on the difference between the mountain and the valley wind regimes could be understood here. And here I took some snapshots. So this is a 10-minute averages of the RHI scans in the transect line. And I'm giving here snapshots for the 2nd of October, which is actually a day where we have a clear sky, as we saw from the valley floor data. And during the morning, what we have is the beginning of the morning, a more unstable regime with a recirculation zone in the lee side of the North Ridge that actually propagates throughout the valley. So that's why we've seen a decrease in wind speed in the morning of the 2nd of October. And we can also see a start of the blockage in the red areas in the windward side of the mountain. So blue is positive radial wind speed. That means flow from the left to the right, and red is the opposite. So we can clearly see the recirculation zone and the beginning of the development of the flow blockage in the windward side of the mountain. This is the same day now. So another 10-minute average timestamp snapshot from the end of the afternoon, where we can see a more stratified flow. So the flow is actually speeding up on top of the North Ridge and also on top of the mountain. And then we can see a really pronounced flow blockage in the windward side of the ALEX mountain. And this is highly correlated with the data in the masts. So it's a good that we have actually data both in the lee side of the North Ridge, in the middle of the mountain, and then in the windward side of the ALEX mountain, as well as the mountain top. So I think the transect line can also gives us this snapshot and clear idea of how the flow behaves during this selected period. Okay, so going for the scanning lidars now, what we are going to see is a small movie that is just a superposition of 10-minute mean reconstructed dual Doppler. So this is the dual Doppler on top of the North Ridge, and the bottom one is the dual Doppler reconstruction on top of the South Ridge. So this is the 2D wind vector that is the projected wind vector in the plane spanning by the two beams. So I would like to highlight that this is not the horizontal wind speed, but is a 2D wind vector projected in the two beams of the lidars. So here we can see a clear difference between the wind regime in the North Ridge and in the top of the mountain. And also we can see that in the top of the mountain, the data availability is really lower because the scanners are really far away, are about 5 kilometers away from the mountain itself. But this is also a proposed validation data that we have. And all these measurements in the Z-shaped transect, they are at 125 meters above ground level, following the terrain. Okay, so this is my last slide, is the more detailed of the proposition of the validation data. So as I told before, I think the first point, it's that we have available measurements of vertical profiles at all of the mass positions. And I have compiled an etcdf file that is readily available in the input data folder. So we have a CSV file with the UTM coordinates of all the masts, and also the UTM coordinates of all the transect, the Z transect. So the CSV file with the mass positions is there. And we also have 3 netcdf files with the time series of 10-minute means of the MP5. So this is the mountaintop mast, the sonic masts distributed along the valley, and the 2 cup masts that are also in the valley floor. So this is the vertical profiles. And the second proposal that we could do a validation after the submission, that's the idea. So this data, these measurements are not available now, is the wind vector, 125 meters above ground level of the Z-shaped transect. So what I have added now is the UTM coordinates of the 167 validation points that are exactly the transect that we saw on the map. So with an output of the 3D vector components, UVW, we can actually decompose the model results into the wind scanner measurements. And the third one, it's the vertical plane on the transect line. Also would be a validation after the submission of results. And the plane, as we already seen, it's the line connected by wind scanner 3 and wind scanner 5. And the UTM coordinates of those systems are in the slide. And the plane, the size of the plane could be related to the plots of the wind scanner itself. So we are using a B2drop, and I think you can see here. This is the folder, the input folder, with the netcdf files of the measurement data, the CSV files with the UTM coordinates. And Roberto now is going to take over to explain the input data in terms of land cover, topography, and also mesoscale inputs. So Roberto, I think you can take over now.
Okay. So hi everyone. Again, thanks for joining for this webinar. I think, can you see my screen? So this part of the presentation is just a further discussion on how we define the case study that Pedro has been mentioning now, and also just to explain a little bit of the input data for the modelers. And again, this is open for the discussion at the end of the webinar if you need, or you find that you need more information for your modeling procedures, and then we can also discuss on what extra data you can need. So just the context to analyze and why we think is important, the coupling between the consideration of synoptic and mesoscale climate into the site is because ALEX is located 100 kilometers to the south of the Cantabric Sea, and then 50 kilometers to the west of the Pyrenees. So it somehow affects, especially during certain periods, the climate of the local climate of ALEX. The selection criteria, as Pedro mentioned, was mostly based on the measurements. So he essentially looked for periods with very high concurrent data among all the sensors. And then we then tried to discard all those periods with very large variability in wind direction, since in this first benchmark we wanted to just consider the microscale effects mainly caused by the orographic elements, which in this case are very well aligned in the case of the Tajonar Ridge at the north and ALEX Mountain in the south, and then also given the wind climate of the sites. Also, we wanted to have a predominantly clear sky base. So based on that, essentially, we just use synoptic and mesoscale data to verify those periods and find one that is very suitable for this. So mostly, we didn't want to have any very extreme or drastic event occurring during the period of these diurnal cycles, like storms or fronts. Also, we didn't want to have a precipitation and particularly at low cloud cover. We looked for low values of vertical wind speed in the mesoscale outputs. And then we also prioritize days with very large amplitudes in the surface temperature or heat flux in order to have more ideal diurnal cycles. And well, also ideally we wanted to have like a relatively homogeneous advection and pressure gradient throughout the PBL. If we look at that specific period, so this is the period that Pedro has been presenting previously. So with this, we just wanted to verify, as I already said, that we didn't have any kind of extreme event on those 4 days. So based on that, we just perform a WRF simulation for that week. In general, we do have the simulation for the entire year. And if you want to take a look at all the details of the WRF simulation, you can check these 2 publications that we've made through the NIWA project. But essentially, this is the WRF setup that we use for this simulation, just with the difference that we just focused or centered the domains on the ALEX experiment rather than on the regions defined at the NIWA production run. But you can check there, and in the links all the WRF setup. Then based on the results so far for that week, I just want to illustrate the velocity outputs for the nearest grid point to the location of 3 of the met masts installed in the ALEX experiment. So in these cases, these 3 lines correspond to the M6 position, so just in the lee side of the Tajonar Hill, MP5, so the mast that is on top of ALEX, and the wind RAS, so essentially the M7 position, which is exactly at the center of the valley. So this is the innermost domain. The configuration, the current configuration of the WRF simulation was kind of typical 2793 kilometer nested domains. So the innermost domain and the nearest grid point means kind of the highest resolution we have for this specific simulation on the prediction of the wind speed at those sites. We can see that there is a clear difference between the mountain top and then the ridge and the valley, though it's interesting that we don't see that shift that Pedro showed in the measurements between the valley and the hill. So that's good. That means that essentially WRF is not able to capture that microscale effects, and those are the ones that we would like to prove that if a microscale or mesomicro approach can figure or can reveal. Here, this box just tries to highlight one of the the periods that we were discussing together with Javier and Pedro about a single, in case of a single diurnal cycle, it's can be simulated because of computational constraints. We were thinking on this second day of the 2nd of October as a potential day, because as we will see, there is a very high winds on the day before, which is the 1st of October, which already guarantees a lot of mixing in the atmosphere, just as a spin-up of the different models. But yeah, I'm just highlighting it here. In this case, I have the same kind of results for the nearest grid point at these 3 positions for the potential temperature at the surface and the heat flux. This is the vertical heat flux from the WRF output. And we also like this day because, as you can see, you have a deeper or very large amplitude during the day and the night. So that means that I think that the stability processes can be more deep, both the stable and the unstable cases. So that can be kind of good to see if the models can capture that. This is just to describe what else we are extracting from the mesoscale model. So for those of you who are not familiar with the tendencies, this is just a brief overview of what we mean by the mesoscale tendencies. This is more detailedly described in these 2 publications, and this is because one of the techniques that we are currently using for simulating the coupling between mesoscale and microscale models is based on the use of this momentum budget and potential temperature budget terms as forcing for the microscale model. So I'm saying this because we plan to provide, or we are providing these terms as part of the input data. And by that, we mean that these are the tendencies. In this case, first, I'm just plotting the velocity and the direction of the WRF simulation at this window, because we found in one of the previous papers that essentially WRF is trying to capture all the local details with all its limitations with the resolution and the PBL parameterization. So essentially, in order to get rid of all the noise that we just want to get rid and then include those with the microscale model, we simply average all the grid points within a window of 45 by 45 kilometer. So we average those values and then we provide as a single column values, let's say, that change on time and on height. So here is how you can see the velocity and the direction along the 4-day period. You can also see that the direction is mostly constant throughout the period. But then here I wanted to show that temperature advection term that I was mentioning before, and then the vertical velocity that is relatively homogeneous. I mean, you can see here something going on the very top of 4 kilometers of the PBL, but I think nothing that extreme. In these figures, you can also see in this case, you do see the pressure gradient and advection terms from WRF, again, averaged in that window of 45 kilometers. So it's kind of smooth. And then I again try to highlight this day between the 2nd and the 3rd of October, where we see like a very strong pressure gradient and advection. Though it's more or less in the same direction, so we hope it's not a problem for the modelers. But then again, nothing extreme. Here I'm just plotting those components, but when you sum up the pressure gradient and the advection, then you get kind of what we refer as the forcing for the microscale model. So essentially, as a mesoscale input data, we plan on providing the data, so essentially three NetCDF files. The first one is these spatially averaged values for the tendencies, as I just mentioned, with the geostrophic or the velocity geostrophic wind, the advection, the temperature potential advection, the potential temperature also with its average along the horizontal space, and then the temperature at the surface, the pressure at the reduced at mean sea level, and the heat flux. And then another 2 files with the nearest grid point from the innermost domain, so the domain number 3 from WRF, at these 3 locations that I just mentioned. So one in the center of the valley, at the ALEX mast position, at the MP5 position, and then one that we consider as the inflow for those who have some methodologies that need like a boundary condition provided as a new condition, as a value, sorry. On the other hand, we have the static data, which is essentially the data that describes the terrain. So in this case, we have the LiDAR airborne data provided by the government of Navarra. So from that, it is obtained the digital terrain model and the digital surface model. So in the right-hand side, you can see the very high resolution data of terrain elevation, which is based on 2-meter resolution. Also for those who need it, you can derive, or there are algorithms to derive the forest height and other features from the terrain above the surface, also at 2-meter height resolution. And then we manually generated a roughness map for all the ALEX complex and even a bigger domain based on Quarry land cover data, and then visual inspection created with visits to the site. And then it's a kind of typical approach for just deriving the roughness. So for this first stage, we just provide this information. For later stages, we can even go beyond with some new techniques to derive the roughness length, more accurate roughness length, especially for heterogeneous sites like this one. And then all the formats and resolutions are summarized in this table. So essentially we provide, as you can see in the link that Pedro has mentioned before, the surface model data based on LiDAR. It's only available in TIFF because probably many of you won't need the surface model data. So we just provide the TIFF and it's a 2-meter resolution. Then we do have the terrain model, so the elevation, in many different formats at 2-meter, which is the original, the raw information. But we also did like a sample of that file for those who really don't need to go that far in terms of the resolution. Then we have the roughness map, which is this map, in these 3 different formats at 3-meter resolution. And then we have extra SRTM elevation data processed in these 3 formats. This data comes in around 80-meter resolution, but we do include the whole Navarra region, so it's a very wide domain that covered by this data set in case you need like very large domains. So we lastly come to the output data. So what we would like to request from the modelers for this benchmark. So as Pedro just mentioned, this is essentially based on the validation data we have. So we want to have these quantities of interest, so the 3D velocity components and potential temperature and turbulent kinetic energy at all the locations of the sensors with this particular format. So it's just the ID of the mast, and then the net. This data should come in NetCDF format. The same for the horizontal planes, which, well, now we can discuss a little bit about it, or we would like to hear from you what you think about the horizontal and vertical planes, so that we can maybe provide you with a grid, and then you just interpolate the 3D values from your domain into this grid in a temporal resolution of 10-minute averages. Average, especially mentioning the LES results, which shouldn't be instantaneous values, but temporally average values. I think as soon as we finish the benchmark guide, we will provide you with a template on the format of the netcdf file, and also some Python script that you can use or you can edit to adapt it to your model's output, just to generate an homogeneous netcdf files with appropriate naming convention and metadata, so it's easy for everyone to process it. So I think we can pass this to Pedro so that we can explain the timeline.
Yes.
Pedro?
Yes, so I think this is a proposal, and I think the webinar can also be a discussion forum, and I can also show my screen here. So we are today in the 4th of November, kicking off the benchmark with this webinar. And Javier, Roberto, and me are working in the benchmark guide that will be published also as a blog post with the details this presentation recorded, and also all the links that we've seen. But I think the most important would be what would be the period of work and submission of results. So we are proposing that everyone can submit something by starting tomorrow. But I think the most important is the deadline that we are proposing to take this benchmark from December, January, February, and between the end of February and beginning of March, that we can close the submission of results, so we can start working on the validation itself in March and April. I also added there, perhaps also start drafting paper together with the participants of the results. And we are aiming for May 2020, where we have the TORC conference that will be in Delft, Netherlands. And I believe, Javier, you are programming IEA Test 31 meeting. So perhaps that would be the perfect opportunity to present the results and discuss, have a panel for discussion. So I believe that's the proposed timeline for now, but of course we would like to hear from the participants. And I think with that we closed the presentation, and perhaps now we could open for questions and some remarks if anyone would like to say something. I'll come back to the timeline. I don't know if we can start with that. Javier, I don't know if you seen this and if you agree.
Yeah, let's leave the timeline while people have a chance to ask questions. So it's like a 6-month period altogether. So I think it's reasonable to expect some results by TORC conference. I also expect many of you coming to this TORC conference and Task 31 meeting, so perfect opportunity to do a workshop on the benchmark. But is there any question before we maybe discuss other details of the benchmark, or questions that we have for you? Anyone with a question? Yeah, as usual, it all seems very clear. No one asking questions. Yeah, it'll take you some time to understand what's requested and what you need to simulate. You'll have to work with data, see if the case is interesting for you. Something I have been discussing with Pedro and Roberto is while we have designed the benchmark with meso to micro in mind and transient models, there's nothing preventing you from participating if you have a quasi-steady state model. And as I mentioned before, we also plan to do another benchmark for numerical site calibration. So maybe you could start working with data from this benchmark, trying to get your model set up in place. And something we thought could be useful is to define some specific profiles during the cycles where we can say that the situation is quasi-stationary and neutral, stable, and then ask the people participating with steady-state models to focus on those specific hourly episodes where they can try to match the profiles at MP5 and see how they get there. As I said, this could be a good way for you to set up your model, because maybe you will be more interested in participating later on in the numerical site calibration benchmark, where it is more natural to expect steady-state models participating. So I don't know if someone was thinking about this in the group with steady-state models that would like to comment on this. No? Okay. Well, probably everyone is into meso micro. Yeah. Something else that we discussed during the presentation was choosing a target day. So it's a 4-day period, but we understand that maybe, especially at the beginning, when you are iterating with your LES model, you may want to focus on a shorter period so that you can try things out. And therefore, we thought of maybe focusing the evaluation on just 1 day. And once everything gets set up, maybe run the 4 days just to get more statistics in the validation data. So we're going to propose one of these days, and Roberto already mentioned which one would that be. But if you would have a different proposal, or maybe shifting that day to get kind of better spin up or anything like that, then we welcome your suggestions. So as soon as you get to know the data, maybe you can send us some feedback about that. The same goes for the output data. We are going to propose a methodology to collect your data based on, first of all, the validation points where we have measurements, but also those vertical and horizontal places where we can have a comparison of the codes, how they kind of reproduce the flow. So we'll in the benchmark guide later this week, we'll publish our proposal for the output data. But if you have other ideas, we'll be happy to know about that and modify the benchmark guide. So essentially, anything we published is editable. So as soon as if we have some better ideas from the group, we'll implement those in the benchmark guide. So during these 6 months, we can have more people joining and contributing.
I think also I'd like to note that if anyone has any feedback on the validation data, and we are just providing just a glimpse of the measurements, but if you think any other quantity could be of interest to have a first look in the 4 days that we suggested, please feel free to drop me an email, and we can also make the validation data more flexible, let's say.
Yeah, and something else that has been useful in the past is when we launch a benchmark, I think it's interesting to have a questionnaire around so that you can tell us what you plan to use in terms of modeling. If you can give us some information about the model that you plan to use, and any feedback you may have on what kind of validation would be interesting in the specific application or research. Just with a question, it makes life easy, and then we can get people registered kind of officially, so we can set up a nice group to start discussions as we progress with the benchmark. Any question that may pop up in your mind?
Hey Javier, this is Elliot from NREL.
Hi Elliot.
For discussions regarding the benchmark, do you prefer email, or have you put any thought into perhaps creating a Slack channel and then we can all have our discussions there?
I've been using Slack with another benchmark, and it was pretty useful. I think it's better to create a Slack project and communicate through Slack. Yeah, good point. And in general, I'm trying to promote that we also share the evaluation script. So as soon as we get to produce that, the best would be to have a GitHub repository that we can share with you, so that by the time you have your own simulations, you can run your own evaluation script. So yeah, as soon as we get those going, we'll share that with you. If you plan to participate and you want to remain anonymous, that's also okay. That's something we will ask you in the questionnaire. So I know for industry folks, this could be the case, that they prefer to remain anonymous, and it's perfectly fine. All the data that you share will be anonymized with a simulation ID, and the idea is that we put all this data in a repository so that we can run the evaluation scripts on those data, and there is no need for us to disclose the name behind the data.
Yeah, I think having a repository of analysis scripts is a great idea, just to have a common discussion point for everybody. Thanks.
Sure. Is there any other question? Okay, so since we are on the top of the hour now, I think it's a good time to close. So we have been recording this session. The idea is to embed this into the benchmark guide that we will publish in a blog post, normally by the end of the week. Together with that, we'll distribute the questionnaire to gather your feedback. And with this, we just launch the benchmark, and as you get to dig into the data, the input data, then let us know if you understand all the data, and then if we can do anything to help you get started. We'll try to organize some frequent webinars as soon as you get going, and we have 6 months to go, so no rush for now, but you can already start. Is there anything else you want to add, Pedro or Roberto?
No, I think that's it. Let's work on the benchmark guide, and I think we can also spread a follow-up email with the link for the Slack channel, the benchmark guide, and also the presentation.
Sure, sure. Also, feel free to ask us or write us directly for any specific, inquiry. But yeah, I think it will be super efficient the Slack channel so that everybody can, comment or.
All right. With that, I think we can close for today. And thank you all for joining, and really appreciate that you have the interest, and hopefully you will have the resources to participate, and will be try to be flexible so you can really commit your work when you can. With that, let's close here. Thank you, Pedro and Roberto.
Thanks a lot. Thank you all.
Bye.
See you. Bye-bye.
Thank you.
Thank you.
See you.
Bueno, la presentación